In this video, we're going to try to understand how polar molecules are determined. So how do you know if a molecule is polar or not? And the reason we do that is that polar molecules have both dipole-dipole attraction as well as London dispersion force. They're both both van der Waals forces, but they're different kinds of forces. Nonpolar molecules only have London dispersion force, which is based on the number of electrons they have. More electrons, the more London dispersion force, as well as the surface area. So the longer and bigger the molecule, the more London dispersion force. The polar molecules can at first seem like they're tricky to tell apart. But polar molecules have one side that's going to be positive, a little bit positive, and one side that's going to be a little bit negative. If it's got unequal electron distribution across the whole molecule, then it is going to be a polar molecule. And so you're going to get this kind of positive side and negative side. It's not a whole charge, but it's a partial charge. A convenient molecule to consider is carbon dioxide. Now, carbon dioxide has got a carbon double bonded to an oxygen, double bonded to an oxygen. The oxygens have an electronegativity of 3.4, and carbon is 2.6. So the electrons are being pulled in equal and opposite directions. And so while the electrons are being pulled away from carbon, the oxygens on each side are equally balancing this out. I like to think of it as a tug of war. Now, if this is my carbon dioxide molecule, is basically these oxygens are pulling the electrons in these two directions. And so this molecule is balanced because the electrons are being pulled towards the oxygens equally. The generic formula for carbon dioxide is AX2. Now, significantly, there's no E. When there's no lone pair, no E at all, then what I want to look at is the whole molecule, and if the whole molecule is going to be balanced, then that will be nonpolar. But if I had an AX2 molecule that had carbon double bonded to an oxygen and double bonded to a sulfur, the carbon is 2.6, the sulfur is 2.6, and the oxygen is 3.4. In this case, this side is going to be negative and this side will be a little bit positive. This would be a polar molecule because it has a side that's not even. So if it has no lone pairs, if it has uneven sides, if it's got even sides, it'll be nonpolar. If it's got uneven sides, it'll be polar. So if I look at a tetrahedral shape, in this case, it's AX4. The AX4 has got electrons being drawn in 4 equal opposite directions. So if they're all the same kind of atoms, it's going to be a nonpolar molecule. But if 1, 2, or 3 of the things attached to it give it an unbalanced structure, then it is going to become, the electrons are pulled more towards one side than to the other side. And so if I had CH4, which has got a carbon bonded to a hydrogen, which is bonded to a hydrogen, which is bonded to, draw it to a hydrogen. Since all of these hydrogens are the same and the electrons are being pulled in equal and opposite directions, this would be nonpolar. But if I had my carbon bonded to a chlorine, bonded to a hydrogen, bonded to a hydrogen, and bonded to a hydrogen, the chlorine is pulling with more force. It's 3.0 compared to hydrogen's 2.2. So this would be a polar molecule, and it would have dipole-dipole force. So anytime that you have no lone pairs, you look at the entire molecule, compare the electronegativities of everything around it, and if it's not balanced, it's polar. If it's balanced, it's going to be nonpolar. That's how you determine polarity with molecules that do not have lone pairs. But lone pairs make this different. Lone pairs give you a side, so this is NH3. And nitrogen has got a lone pair and it's bonded to 3 hydrogens. Because of this lone pair pushing this down, it's got a nitrogen side and then the hydrogen sides. The hydrogen sides to this are going to be less electronegative than the hydrogen. So this will be polar because this is 3.0 and these are 2.2. So the electrons are being pulled towards the nitrogen. The only way that you can have lone pairs on your central atom and not have it be polar so that it becomes a nonpolar molecule is if you have the exact same electronegativity attached all the way around. So phosphorus is 2.2, hydrogen is 2.2, and so there are no actual polar bonds. If there is no electron unevenness, this will be nonpolar, even though it's AX3E. This is H2O2. And H2O2 almost looks like it's even, right? It looks like it's got a plane of symmetry here. And if we looked at it this way, it looks totally even. But it's a three-dimensional molecule, and it also moves around. H2O2 is AX2E2. It's got the E2. So as long as these things are uneven in any way, so oxygen and hydrogen, which are very different, it will be polar because it can also take shapes that you might not have drawn. So if you follow this rule, you should be able to decide if the molecule is polar or non-polar. All polar molecules have dipole-dipole force and London dispersion. Non-polar molecules will only have London dispersion force.